Hello and welcome back, Function Transformations. Today we will be combining transformations. We've looked at translations where we move things left, right, or move them up, down without changing the shape of the graph. And we've also looked at stretches where we kind of contort things, we stretch or we compress, and reflections where we flip things perhaps upside downsies or a left-right reflection. We're going to be combining all of those. When we do so, there is a certain order of operations that we have to maintain. Just like when you're performing operations, multiplication has to happen before addition. Same here, where when you look at A and B as multipliers, they're attached through multiplication. And those have to happen before subtraction and addition take hold. So there's an order listed here. It says you must apply the vertical stretch or compression, apply the horizontal stretch or compression, and then apply the translations. Worth noting, however, is that, work for me, is that these stretches can happen in either order. Whether you operate horizontally or vertically first, that's fine. And contained within that is, of course, the horizontal and vertical reflections, because they'd be contained in A and B as well. What really matters is after you do those, in whichever order you so desire, these translations are always last. Personally, I prefer to do this really step by step. If you want, you could even combine the horizontal and vertical stretch at once. It's not for everyone. It would be faster perhaps, but I'm a fan of doing things really step by step, breaking it down. I'm also a fan of describing all the changes we expect to see. So if we look at an example like this, where we have to graph that function based on this original, I like to describe what's happening. Like this 1/2 over here tells us that we'll have a vertical compression. And then this 2 over here tells us something horizontally. It looks like it's multiplying, but we know anything horizontal acts oppositely, so that's also a compression. And then there's this -1 and this +2. The shifts I have happen all at once, the translations. So we have to shift 1 to the right and 2 up. Those are the transformations you have to employ. And I will have them happen really step by step, one at a time. It's worth noting some points that exist, because those are the points we'll be manipulating. So anything where you can find a lattice point or a point with more integer coordinates, that will be helpful. And we can work from there. So vertical compression of factor 2, I'm going to divide all the y values by 2. Like this point, which was at -5, -6. This -6 is going to change and give me -3 instead for that point there. And I'm going to do that for all these points. So over here, we had a y value of 3. Now that gets cut down to 1.5. Up here, a y value of 4 is now just 2. And going similarly across the board here. How far over is that? Here. When we connect the dots, we're not going to use a solid line. This is not our final graph. We're not done this yet. And to indicate that, we're going to use dotted lines. Dotted lines say this is involved, but it's not the real deal. That's the pink one. Done. So now I'm going to apply the horizontal compression. I'm going to take all these already transformed points and play with just their x values. I'm going to divide their x values by 2 because of this. So over here, where x was -5, that'll now be -2.5. Not the most beautiful point I've ever seen, but we'll love it all the same. Over here, this becomes -1.5, -1.5, 0. So note the y values are staying the same, it's just these x values are getting pushed in. This is still not our final graph, so we're still just using dotted lines. And then with that being done, we can finally move on to these shifts. Every point is going to go 1 to the right and 2 up. So this point here is going to go 1 right and 2 up. And this point here is going to go 1 right and 2 up. And every single point is going to go 1 right and 2 up. Always 1 to the right, 2 up. So a consistent shift for every single one of these points. Bop. And this one is our final graph. This is the last transformation we have to have employed here. So now we can use a solid line or curve. Noting that the original graph had arrowheads at either end, so we must make sure we're using the same on this one. We're going to quickly talk about mapping on the next page. And the mapping formula that you'll see there is a little gnarly, to say the least. It's a good color these days. Yeah, it's a nice gray. Why not? I don't like thinking of it in terms of formulas. Again, descriptors are kind of where it's at. When you have something like y equals AF of B times x minus h plus k, you can ask yourself what happens to x. Ask yourself what happens to y. Look at them separately. If you look at what happens to y, it gets multiplied by a. And then we add k. Boop, boop. What happens to x? Well, we don't multiply by b. It's tempting to say that we do. We divide by b. Acts oppositely. And this acts oppositely too. We're not subtracting h. We're adding h. So when we look at that, x turns into x being divided by b plus h. What happens to y? We take y, we multiply it by a, we add k. So on this next page where we see this kind of more formulaic style of here's what happens to it, it's not the prettiest. I mean, if you want to memorize that, go for it. But just make sure you can describe what's going on with every transformation. Because if you can do that, again, you can do anything else. We're going to apply our knowledge of transformations to this last example here. And it can be a doozy, but we'll look at some tricks we can use in... Oh, that's a good color. Sure. We can tell that things have happened. We can tell that this thing is way higher than it used to be and a little bit offset to the left too. We can tell that there's a gap between these 2 points that's completely different. So there must have been stretches involved as well. Probably no reflections because nothing looks like it flipped. But stretches and translations. let's figure out what stretches happened. I'm going to look at the vertical stretch and the horizontal stretch, but how to do that? What you can look at is the gap between the endpoints. And if I'm looking at it vertically, and I'm saying this went from down there to up here, originally it changed by 2. Whereas in the new function, the gap between the top and the bottom is 4. How did we turn a gap of 2 into a gap of 4? We must have multiplied it by 2. So we can safely say that there's a vertical stretch factor of 2. If you want, you can try and do all the rest. Again, you have the freedom to pause whenever you want, so you could do that. I'm going to proceed like right away. I'm going to figure out what this does horizontally, because originally from left to right, this whole function only had a gap of 4. Now, from left to right, this whole thing has a gap of 12. So to turn a gap of 4 into a gap of 12, I must have multiplied by 3. So there's a horizontal stretch factor of 3. What I might recommend doing at this point, and you don't have to, there's a number of ways to proceed, but I'd kind of transform this original f of x and see what I get. If I employ a vertical stretch factor of 2, I get this. And if I employ a horizontal stretch factor of 3, multiplying all the x values by 3, 3, 6, 9. I get that. And we can see that it looks pretty close to our final graph. We're just missing that translation piece where we have to take these points and go up 1, left 3. This one has to go, up 3, left 1, up 3, left 1, up 3, left 1. And if we do that, we'll be complete. Up 3 and left 1. There are other ways to do that. I did this with 3 key points, 1, 2, and 3, to figure out how they translated. You could really just do this with 1, and that'd be fine as well. Right? Take 1 point, say it gets stretched by a factor of 2 vertically, stretched by a factor of 3 horizontally. What do I have to do to get it to be its corresponding point on the new graph as well? That's fine. There's multiple ways. But if we can describe these, then we can get our values of A, B, H, and K. Because there's a vertical stretch factor of 2, we can say that A is 2. Because there's a horizontal stretch factor of 3, we can say that B is not 3, but 1/3. Looks like division, but horizontal things, so it effectually gives us multiplication. And then our shifts, we went left 1, so H is a -1, and K is up 3, so up 3. Putting it all together, we can say that g of x is equal to some transformation of f of x. I'm going to take 2 f of x's, but modify it even further. A +1 in here to say that we had to shift left, and then +3 over there to say we had to shift up. That is done. That is the conclusion of this section of notes. There are still notes on function transformations. We're just not there yet. We will be in the next video, if I had to guess. I'm not a guessing man. So if you have questions, comments, concerns, please contact me. Let me know in class or outside of class. There is, of course, practice work to practice with. So give that a shot. Give it a go. Give it a stab. Give it a whirl. Give it a try. Give it a full attempt. All your muster. And as always, believe in yourselves. Believe in the dream. It's been a Slice By.